Hello everybody. So now we are going to talk about the second parameter, which is the enthalpy, and we will see how it's affected by the temperature. So we are going to do a very similar approach like what we did in the internal energy. So we know that the enthalpy is dependent on the temperature, and we can get the slope for a very small change in the temperature at this point. So this is going to be the slope, which is delta H over delta T, and as we said before, it's going to be variable from one point to another because it's a curve, not a straight line. And from the slope, which is delta H over delta T, if it approaches to zero, if this delta T approaches zero, then this is going to be the differential of enthalpy with respect to temperature. And we found that this differential, which is partial H partial T, or partial H hat partial T, at constant pressure, we call it the specific heat capacity, but this case it's at constant pressure, not at constant volume like in the case of the internal energy. And this is the only difference. Everything else is going to be the same. If you are interested in getting the delta H or dH, it's going to be the Cp dt, and of course Cp is function of temperature like Cv as we saw last time. And if we want to get the change in enthalpy, we will do the integration between T1 and T2, and this is how we get the change in enthalpy from T1 to T2. The cases of delta H and delta U, or I mean in case of delta H, this is wrong. I will fix this. This is delta H, not delta U. So in case of delta H, in case of changing pressure, so we said here that this is Cp, which is heat capacity at constant pressure. So if the pressure is variable, then we need to take this into account. So we will do the same as we did before. So we will break this change in enthalpy into two changes, like a hypothetical path, like we said before. We can do this as delta H1, where we have only change in pressure, and then we have delta H2, where we have change in temperature only. And the total enthalpy change is going to be the summation of delta H1 and delta H2. And in this case, we have we know for case number one that delta H, this is delta H, not delta U, I'm sorry, it's a mistake. So delta H equals 0 for ideal gases, for liquids, and for solids. I mean, no, this is right. This is delta U is equal to 0 for ideal gases, liquids, and solids. So it's going to be the same if we have ideal gases. If we have non-ideal gas at constant pressure, this applies as well. So it's going to be the same, but for liquids and solids, delta H is not equal to 0 if the pressure changes. And this is what we mentioned before, that it's going to be equal to V hat multiplied by delta P. And we said V hat is almost constant because they are incompressible. So this is going to be this part. So this is delta U is 0. It's not delta H. Delta U is 0. Delta H is not equal to 0 for changes in pressure for solids and liquids. So this is going to be the first part, which is delta H1, and this is going to be the second part, which is delta H2. So to summarize all what we mentioned about the effect of pressure and temperature, I think this table is going to be very helpful, because this table, I tried to summarize everything we mentioned till now. So we have the effect of pressure at constant temperature for the delta U and delta H, and here is the effect of temperature at constant pressure for delta U and delta H. We have for each one of these cases ideal gas, non-ideal gas, solids, and liquids for the two parameters. And we see here that for the change in internal energy and change of enthalpy, it's almost not affected by pressure at all for the cases that we deal with, for ideal gases, for solids and liquids. For non-ideal gases, when it's close to ideal conditions. We mentioned before that non-ideal gases are very hard to describe, and they require very complicated equations, and in this case, or this is not going to be within the scope of our course. So this is the case that we are going to deal with. So we can say that we deal only with ideal cases, just to instead of saying it's non-ideal but it's close to ideal condition, it's an ideal case. And for the ideal gas, delta H is equal to 0, and the only case that's not 0, which is we have delta P, and we will see later when we do some calculations that even this parameter or this value is usually very small compared to the effect of temperature on the enthalpy. Okay, and this is what we saw before. That its effect is very minimal compared to the effect of temperature. So this is the summary of the effect of pressure. For the effect of temperature, it's almost all of the internal energies are CVdT, the integration of CVdT, and for all the pressures, it's almost it's only CVdT and CPdT. And we said that if we have multiple cases or the combination of pressure and temperature, this is the only case that we have. Let me zoom in here just to make it clear that this is the summation of these two parameters. This is the only case where we have more than one term in the equation. So this slide summarizes everything. Now we know that these are the equations that we are going to deal with. Now there is a very important question. Now we know that we are going to go through the integrations. The question is, what are the mathematical formulas of the CV and CP? Because this is what we are going to do the integration for. If we don't know the mathematical formula, this is going to be only some theoretical equations that we are looking at. So we need to know how to get the values of CV and CP, or the mathematical formula, because we say it's CV as a function of temperature, CP as a function of temperature. We need to know what is the mathematical formula that we need or we are going to use. And this is going to be what we will discuss in the next video. Next video is going to include a lot of details about this. Because the table contains, this is the table that we're going to be dealing with. It contains a lot of information, and I'll make the next video just to discuss this information in details. So we'll continue next time, inshallah. See you then.